9.3D, we're going to recognize paired data and use a one-sample T procedure to perform significance tests for that data. So what is paired data? We've actually looked at it a little bit back when we did the Coca-Cola example, when students were asked if caffeine impacted their pulse rate. There's two ways to do paired data. One way would be to make two observations on the same individual. Again, if I was seeing if Coke made a difference to me, I would make one observation before I drank Coke. I would drink the Coca-Cola. I'd make a second observation. I am the paired data. I'm the same individual, but two observations. In that case, it's a single sample, but measurements are done twice on that person. A second way to do paired data is to actually have it be one observation each of two similar individuals. So what I would do is match two people that are very similar to each other, and maybe if it was a drug test, for example, I would give one person drug A and a second person drug B. If they were about the same height, the same weight, the same age, I can compare the results of these two people as one unit of data. So how do you actually get ready for the procedure? What you're going to do for a paired T procedure is the paired data results from measuring the same quantitative variable twice. You're going to take the data from the two different elements and you're going to analyze the differences. And this is the key here, is you want the differences. You ultimately want to create one set of data. So if we were looking at the Coca-Cola example, I would take my beginning pulse rate, my ending pulse rate, and then I would compute the change in my pulse rate, and I have one piece of data for me. That's your goal. So with that, you can then use the one sample T procedure just on the computed differences that you create. So you're going to have to decide if you have two individuals, for example, do you keep them separate into sample 1 and sample 2, or do you crunch it together into one final sample of the differences? And we will talk a little bit more about that example in Chapter 10. Let's look at this one example where it is paired data. It says here, for the second semester projects in AP Stats, Libby and Catherine decided to investigate which line was faster at a supermarket, the express or the regular lane. To collect the data, they randomly selected 15 times per week, went to the store, bought the same item. However, one of them went to the express and one went to the regular. To decide which lane they would use, they flipped a coin. If it was heads, Libby used express, Catherine was regular. If tails, they would reverse it. They entered randomly assigned lanes at the same time and recorded the time it took for each transaction. So here we have the express lane, the regular lane for each visit. Carry out a test to see if there's convincing evidence that one lane is faster than the other. Well, folks, we could actually take this data and create a new set of data. We could compute the differences, which would basically, if you think about it as a one variable stats to get some mean and standard deviation data, we could create one new list of list 1. So in this case, what we would see is we could create one observation with two similar individuals and get one new answer for each. Now, what would your hypothesis be for this? Well, first thing, I'm going to come on here and define my alpha. Let's just go at 5%. And I want one set of data, so I'm going to state H sub O and H sub A. Now my H sub O, I think that the mean difference between the two lanes, and I'm going to call it mu sub D, is equal to 0. However, what do I really think is the difference? Well, it depends how I'm going to calculate that. So let's define what mu sub D actually means. And as long as you define it and stick with the same definition, you'll be fine. I think that if I do the regular lane minus the express lane, that the mean difference is actually going to be greater. So mu of D, I think, is going to be greater than 0. Again, let's define that. So that's going to be, I'm going to say the true mean difference in time from regular minus express. So in this case, because I say regular minus express, I suspect it's going to take longer, so it would be greater than. Now, if you reverse this calculation, your hypothesis would be the mean difference is less than 0. So again, as long as you define this one way and you write it appropriately, you'll be fine. For my plan, what I'm going to do is I'm going to perform a paired t-test for mu. And I could say one sample paired t-test if I wanted to, but the paired implies it will be one sample. Were things done randomly? A random sample was selected to make the purchases for the lanes, so we're good with that. For independence, we are not doing replacement, so since the randomly selected times to conduct the study are from a finite number of possibilities, the differences should be independent. So we could say 12 times 10, there's going to be more than 120 visits to this store, so that's fine. Now for normal C, our sample size was only 12, and I don't know if it's coming from a normal population, and our sample size was small, so we do need to graph this out and look for differences in normality. Now here I have a couple different graphs. We have a dot plot of the differences. We have a box plot of the differences. And we also are going to see a normal probability plot here. Again, don't worry about doing all three of these. It's just good review. At least do one of the dot plot or box plot. Here the dot plot and box plot are slightly skewed to the right with no outliers. So the normal probability plot looks roughly linear, so that's fine too. And it's reasonable for us to use the t procedures and assume it's approximately normal. Now, be thoughtful, how were these graphs actually made? Again, if it's the differences, what they did is they took the paired data and they subtracted it and they got a new column of all of the differences, right? It was regular minus express. So you're going to have 12 pieces of data with differences, and that's what was plotted. And that's how you actually do this test. So once I have my 12 differences, I'm personally going to put them in my calculator in list 1 and then do a one variable stat. If I do that, the mean difference is 42.7 seconds and the standard deviation is 84. My test statistic, because it's the means, it's just going to be my sample minus my hypothesis as it was 0 over the standard deviation over the square root of the sample size. And sorry, I guess it was sample size was 15 and not 12 I had mentioned earlier. Our test statistic is 1.97. Now this was a one-sided test. We think it's actually going to take longer, so we're looking for the tail on the right. So if we compute the p-value for that, what we're going to end up getting is we have to use 14 degrees of freedom because it's a t-test and the sample size was 15. The p-value is 0.034. Keep in mind, again, if you use the calculator, we're just going to go to stat test. And which one do you select in this case? It is actually called just the t-test. There's not a real specific detailed title for this one on the calculator. And you'll put in the information accordingly, and you should get the same result. Let's make our conclusion with alpha being 5%. We're going to say since the p-value is less than alpha, that is 0.034 is less than 0.05, we reject the null hypothesis. And from there, we can conclude there is convincing evidence that the express lane is actually faster than the regular lane, or conversely, that the regular lane is slower than the express lane, what you could also say. Now, we finished all the content with Chapter 9, so let's bring it all together in one big slide here. Again, I did give you that handout to use for Chapters 8 through 12. This is even a few more details. So what is the name of the particular test? Here are the various names that we did. We have the one proportion z-test for p, the one sample t-test for the means, and the one sample t-test for matched pairs. Really, these two are the same. What would your hypotheses look like for that? Remember, in writing your hypotheses, there's a variety of different ways you could do it. For the proportions, we are establishing that p is equal to p naught, and then we're going to either do a one-sided or two-sided test for h sub a. For the means, our mu is equal to mu naught, and again, one of the three tests. And the only difference here is the mean difference for the matched pairs. So notice here I say mu, and here is mu sub d. It is really important that you do this little subscript, or you actually write the word difference, or you call it something else, so we know it's the differences. Now, in terms of the conditions, the random and independence is obviously going to be the same for all three of these tests. It's just that normalcy condition is different depending on which one we do. For the proportions, remember for the tests, we're using p naught, and it's n times p and n times 1 minus p are both greater or equal to 10. For the means, we're either knowing that the population is normal, which makes it good. We either meet the central limit theorem of being greater than or equal to 30, or we know the t procedures are not robust, so you have to graph it out and look for little to no skewness in outliers for both of the means tests. In terms of the mechanics, again, as long as I have stated some of these words up here, I don't necessarily have to show these statistics. But what do you need to write down for calculator speak? Be careful. We do want to see the p-value for this. You need to talk about the degrees of freedom in the p-value and the degrees of freedom in the p-value for your matched pairs and for the means. The conclusions for all three of these are really the same thing. Remember, compare your alpha, show your p-value numbers, either reject or fail to reject, and conclude H sub A or not conclude H sub A. Never, ever conclude H sub O. Be really careful with that. Now let's wrap up by looking at some examples about how to use your T procedures wisely. Let's look at another matched pairs. Suppose that a large high school district implemented a new math curriculum for the school year. To see if the new curriculum is effective, the district randomly selected 500 students, compared their scores on the standardized test after the curriculum changed to the score on the same test before the curriculum change. The mean improvement or the mean difference is 0.9 and the standard deviation of the difference is 12. Calculate the test statistic and p-value for the test where the mean difference is 0, but we think the mean difference is greater than 0. So to do that, the statistic, just remember the key features to it, are going to be your piece of data, your results, minus the hypothesis over our standard deviation of the sample and square root of sample size. That is our t-value. Therefore, we know this is a greater than test, so we want the p-value that's greater than. So I can just use TCDF, a lower bound, upper bound, degrees of freedom, and that's our p-value. Well, if we're looking at a significance level of 5%, are the results considered significant? Well, think about it. In this case, P is less than 5%. Therefore, we would reject H sub O and we would conclude H sub A. Does that mean significance? It does. Since the p-value is less than 5, the results are significant at the 5% level. The improvement was larger than we could expect to happen by chance. However, an increase of 0.9 points may or may not be practically significant. So it wasn't a huge increase in the reality of it all, but it was somewhat significant statistically. Part C, can we conclude that the new curriculum is the cause of the apparent increase in scores? Now, remember from Chapter 4, in order to make cause and effect conclusions, an experiment must have taken place. So in this one, be really careful. No, even though the increase was statistically significant, we cannot conclude that the new curriculum was the cause. There was no control group for comparison and no random assignment of the actual treatments. So we have to have a true experiment going on in here with the random assignment and control group for this to actually work. Look at this caffeine example. When an AP Stats class did the caffeine and pulse rates experiment, remember we just talked about it, the confidence interval for the difference in the average pulse rates was right here. It's our confidence interval. This means that drinking soda with caffeine can increase your pulse rate by as much as 4.59 right here, and decrease it as much as 2.52, which is the lower end, compared to drinking soda with no caffeine. It seems likely that caffeine does have an effect on pulse rates, but we need more data to estimate this effect with more precision. What you just want to be cautious of is this right here. That with some research, small differences are only detected with larger samples. So to ensure tests have a high enough power to detect the differences, make sure you have a high enough sample. So ultimately, when I did this caffeine experiment in our class, we only had 20-some people. I'm not really sure if that's a large enough sample for our case. Remember, the t-tests for the means are not robust against small sample sizes. So even though we can perform the test because it might meet the normalcy requirements, you just want to be cautious if your sample size is large enough. This GPA example here, suppose that you wanted to know the average GPA for students at your school who are enrolled in AP Stats. Since this isn't a large population, you conduct a census and record the GPA for every student. Is this appropriate to construct a one-sample t-interval for the population mean GPA? Now, again, what they did is they surveyed the entire school and they say a census. I do want to talk about a census for just a second, though, because you might see it on the AP exam. You would want to say here, no. If we have GPAs for every student in the population, we can actually calculate the true mean. We only use confidence intervals to account for variability caused by random sampling or random assignment of treatments. If you ever read anything about a census, it's absolutely pointless to do statistical work on it because a census means we have the actual population data. In this one here, more cell phones and brain cancer example. It says here, suppose that 20 significant tests were conducted and in each case the null hypothesis was true. What is the probability that we avoid a type 1 error in all 20 tests? First of all, be careful, right, that the null hypothesis was true. Well, if they have their population, they can say that, but we never say it was true. They're basically saying they can't reject the null hypothesis. But this is a good question about the probability to avoid type 1 errors. Remember type 1. If we're using a 5% significance level, each individual test has a 0.95 probability of avoiding type 1 error. The type 1 error is our significance, so that is the type 1 error. To avoid a type 1 error is a 95% chance. Okay, we have 20 tests, and we want to avoid the type 1 error, so we're looking at 95% probability. Well, assume independence. Therefore, the probability of avoiding the type 1 error in each of the tests is 0.95, 0.95, 20 times. The probability to avoid that is 36% chance. Now, do keep in mind, if you didn't want to do the probability this way, which works great because they're independent, this is a binomial situation, so I could do a binomial PDF. I could do 20 elements at a 95% chance of success, and I'm picking all 20. It's 0.36, so just another way to come up with that. So what does this ultimately mean? This means there's a 64% chance we will make at least one type 1 error in these 20 results. Finding one significant result in 20 is not a surprise. So we need to be cautious that we could have a 64% chance we make just at least one or more type 1 error in these tests. So even though we're doing multiple analyses doesn't mean we're getting away from making any type of type 1 errors. So let's wrap up the chapter with our case study at the beginning. We said, do you have a fever? They were investigating if the human body temperature is really at 98.6. So they surveyed and studied 130 people at random, ages 18 to 40. Here's actually the results. They have the mean temperature, standard deviation. They also have the one sample t-test information right here. We can tell that they tested that mu was equal to 98.6. They want to test H-sub that it's not. Here is the confidence interval that came out of it. Here is the test statistic. Here is the p-value for that. Now notice the p-value is pretty much 0. So since the p-value is 0, we have strong evidence to reject H-sub and actually conclude that the mean body temperature for healthy adults at this age is different from 98.6. If we take a look at this confidence interval that they have constructed, we can tell it's 95. So we are 95% confident that the interval between these two values contains the actual mean body temperature of our healthy adults.